Welcome to 5G Technology World. I'm site editor Martin Rowe. 5G's millimeter wave signals and the higher frequency so-called sub-terahertz range that is now undergoing research for future generations of wireless all suffer from attenuation and blockage as they travel. A technology called Reconfigurable Intelligent Surfaces, or RIS, also called Reflecting Intelligent Surfaces, Large Intelligent Surfaces, Smart Repeaters, and Holographic Radio, is under study as a way to redirect and amplify signals around buildings and bring those signals indoors as well. On October 4th, 2021, the European Telecommunications Standards Institute, or ETSI, announced the formation of a group dedicated to specifying how these surfaces might perform. What's the concept behind reconfigurable intelligent surfaces, and how will the group function? To find out, we spoke with Dr. Arman Shojaieffard of Interdigital Europe, chair of the ETSI Industry Specification Group on Reconfigurable Intelligent Surfaces. Arman, thank you for speaking with us today. Please tell our viewers about the technology behind reconfigurable intelligent surfaces.
It would be good to look at each term individually. So these are surfaces that can be engineered. They typically have properties to do with the shaping of the electromagnetic waves. So this could be refraction, reflection, absorption. And then you have intelligence, the term intelligence referring to the fact that you can adapt the response of these surfaces in a smart way in order to achieve a certain benefit. And then the term reconfigurable points to the fact that you can in real time or dynamically adapt this response. So putting all of this together, RIS is a new type of network node which makes use of these smart radio surface technology. And the benefits of having these types of nodes, which are different to, let's say, your conventional type of network nodes. So these are, for example, fully stacked cells like your massive MIMOs, your millimeter wave access points, different to relays where you might have decode and forward relay, or you can have amplified and forward relays. RIS is essentially different to all of those type of deployment solutions in terms of the associated characteristics it has in terms of reconfigurability, adaptability.
What are the characteristics of reconfigurable intelligent surfaces, the challenges to overcome, and its potential benefits?
A key characteristics of these surfaces is that they are, for the most part, passive. So, for example, you could have an electromagnetic sheet of these scattering elements or unit cells, as we call them, which are mostly passive, and the hardware required to if you like, tune these elements could be quite primitive. So you could technically control or adapt the response of these elements by having, let's say, a simple microcontroller as far as the software and hardware requirements are concerned. So This really sets it apart from your, again, conventional ways of doing things, of, for example, utilizing phased arrays or utilizing active antenna systems, where you have extensive hardware requirements in terms of end-to-end transceiver chains, in terms of baseband units and advanced signal processing components, and which lead to a number of challenges, including weight, including energy consumption, including complying with the electromagnetic field regulations. These surfaces essentially provide a lot of benefits as far as those aspects are concerned, and these characteristics allow you to integrate these surfaces with day-to-day objects. So these could be walls, these could even be windows. So we see some early prototypes of these technologies being transparent mirrors that reflect and, let's say, focus signals in a certain way. And one of the key benefits of having these characteristics, as I'm sure you've seen in the literature, is around improving the coverage performance of existing systems. So you could distribute these surfaces onto walls, particularly in indoor environments, in order to achieve coverage enhancements from existing systems.
You mentioned microcontrollers. What role do they play in tuning the reconfigurable surfaces?
They could play the role of adjusting the response of the surface, for example, these metamaterial or scattering elements. What actually allows for the intelligence here is the signaling link from the microcontroller back to the network, and this is a key term in the terminology of the RIS technology, reconfigurability. So it is, for example, the network controller that sends instructions to the RIS microcontroller in terms of how it should change its response at, let's say, any given point of time. So it is through that signaling link that we can achieve that vision of turning the environment from an obstacle to essentially a smart wireless environment where we can dynamically tune and control RF signals in electromagnetic domain, so what we call layer 0. What we see today is only early prototypes for what RIS could potentially look like. So we're very much still in the early R&D phase of the technology. We have seen a number of prototypes, and quite varied in terms of the architecture, purpose, frequency range, all these kind of different aspects that one needs to consider when you actually design and deploy such a technology. And therein, in terms of the sizes, we see very much depending on what your end use case is, the size and shape and characteristics of the RIS can be changed. So one example is that, of course, you could have RIS on sides of the buildings, and you can have, if you like, very, very large surfaces with, many thousands of small radiating elements there to really, for example, focus the response of the surface onto a specific direction, and but also at the same time, a lot of the benefits that one might want to get can be done with much smaller surfaces. So in terms of the size, it very much depends on what the use case is, what is the enabling technology. But what we see today is that these could be quite reasonably sized surfaces, let's say a square shape, a couple of meters long in each direction. And then also in terms of the aspect that you mentioned, for example, around blocking sunlight, these surfaces could even be transparent, as we discussed. So these could actually look like mirrors. So windows could potentially be used to enable RIS functionality in the future.
Do you envision RISC being used for millimeter wave and then higher frequencies as 6G comes along? Or do you expect this to be at the lower, I'll call it sub-6 for the moment, frequencies?
Yeah, RISC, the answer is indeed both. In the literature, I would say there has been a strong focus around utilizing these RISC components to facilitate operation in even higher frequency bands beyond millimeter wave onto sub-terahertz and terahertz. But what we actually see and are asked by the operators is how these surfaces could be used to improve systems KPIs in sub-6 gigahertz bands as well. So that is one key use case for a lot of operators that are quite keen in this technology. So within the work of the ESTI RIS, one of the key activities that we have is to identify the use cases and deployment scenarios for RIS. And therein, we're looking at sub-6 gigahertz bands all the way up to terahertz bands. And these, of course, might have different use cases and functionalities, but indeed, I see the technology to be quite important as far as, let's say, the evolution of the 5G is concerned. So 5G advanced, so release 18, release 19, and we see already some proposals from the industry and intention to look at aspects such as smart repeaters, and they're very much, if you like, fit within the category of RIS. And they are intended to work on sub-6 gigahertz bands and existing millimeter wave bands in 5G. But we also, of course, see RIS as a key enabler for future systems, including 6G, and enabling operation at that even higher frequency bands.
I assume we're talking about these surfaces as some sort of panel. Who would install these? And would they block sunlight in buildings?
In terms of how these surfaces can be designed and made, as you say, this is an open area of research and development. We see a number of, if you like, directions towards this. One is, of course, metasurface technology, so utilizing metasurfaces with elements that are very much closely spaced between each other. So, thousands and possibly many thousands of elements. But we also see more, if you like, conventional type of panel designs where you have these small antenna elements, if you like, spaced in the usual way of half a wavelength apart in order to achieve certain directivity. So this is, I guess, two approaches that we see today in terms of how these surfaces are being manufactured. But also there are hybrid versions, and I'm sure there will be other possible ways of going about designing them as well. And again, this is another aspect of the work of the IHG RIS to understand what is the state of the art as far as the microelectronics components of these surfaces are concerned.
Armand, can you explain the structure of the RAS group within ETSI and some of its goals?
So the work of the ETSI IHG RIS officially began on the 30th of September with a kickoff meeting. The way that we work in the group is very much similar to the other ETSI ISGs and standardization bodies, where we follow a contribution driven consensus-based approach for delivering on the work of the ISG. In terms of the deliverables of the group, we are targeting what are called the group reports, where these will be, if you like, documents where we have properly documented everything that we have found and reached consensus on to do with the various aspects of the risk technology, and some of the key aspects that we're looking into are, as discussed, what are the use cases and deployment scenarios for RIS. So RIS has a large number of benefits on paper, but this technology will certainly not be a solution to all problems. Rather, this is in our view one potential key solution that can be leveraged to specific use cases. So that's one important area. Another important area is the channel models and evaluation methodology for this technology. So as you can imagine, when you talk about all these complex environments with many thousands of radiating elements whose response that you can change, we very much need to revisit and fine-tune what are the channel models for this technology. And also importantly, we will be documenting any gaps within standards that we see that are required to enable and, if you like, fast track the eventual commercialization of the technology. So the ISG very much works to be a, if you like, an enabler for the technology in terms of bridging the work from, if you like, pre-standards, so the research phase, onto standards work.
Who are some of the group's participants and members?
We're very pleased to have a very diverse group of members and participants. So we have key operators involved in the group, the likes of British Telecoms, the Orange, Telecom, Telefonica, and we also have a number of vendors, but also very importantly, we have a large number of key university partners who have been working on risk technology for a long time, and this initiative is intended for them to be able to bring some of the great work that they've done onto the standards.
You mentioned use cases. Can you be more specific as to what kind of use cases you might anticipate?
Yes, so we already talked about coverage, and I would say I see that as a key use case for risk, especially in perhaps the short to medium term. So one use case for the technology could be improving the indoor coverage performance of 5G deployments.
What kind of research is needed with regards to materials from which these surfaces might be made?
One of the main use cases for risk could be to use it as let's say, as intelligence reflector. So that's one possibility. But so that we already see that as a key use case in early proof of concepts. But the properties that these surfaces may have could go well beyond just doing, if you like, reflection. So, for example, you could use these surfaces in order to absorb energy, or you can use these surfaces to if you like, narrow or direct beams in a certain direction. You could even potentially go even further, where you encode information onto these RIS elements, where you could achieve certain, if you like, transmitter capability as well, what is known as holographic MIMO. So this essentially goes beyond just using these surfaces as a mean to reflect RF signals, although that could be one key use case.
After the group reaches some consensus on the technology, will ETSI then work with other standards organizations such as 3GPP?
Indeed, the work that we do in the ISG RIS will be very much complementary to the work, the existing work of ETSI, including us having relationships with ETSI bodies and industry organizations, such as the 3GPP. And the intention here is to avoid any duplication. The intention is to maximize synergy and essentially have a broad industry adoption for the technology. So we're very much going to be working very closely with the other groups in order to achieve all these items.
Do you have a timeline for when this group might reach consensus on the technology and its use cases?
The intention is indeed to reach consensus around what are the key use cases for this technology, what is the state of the art, what are the gaps within standards, what are the requirements that need to be met as part of the work of this ISG. So I would say, let's say in 2 years' time, after the duration of the ISG is concluded, we would have views on all these aspects of RIS technology to then share with the outside world.
Arman, thanks for meeting with us today to discuss reconfigurable intelligent surfaces and how they might help us improve our high-frequency wireless communications. For 5G Technology World, I'm site editor Martin Rowe. Thank you for watching.